Okay, so let's continue now, and let's see this. I want to try to understand some so-called asymptotic behavior. So something like from omega that goes to 0 and omega that goes to infinitive. So let's look at this. So because the low pass filter implemented by beta of omega will have a transfer function that goes to 0 for omega big, then 1 over beta of omega goes to infinitive for big omegas, which means basically that this is our amplification factor of our amplifier. So for big omegas the amplification is infinitive, which is not a number. So if we go here, this is why we need those two resistors in order to limit the possibility that this transfer function will become infinitive for high frequency, or let's say, better saying, we don't want this amplification to become extremely large for large frequencies. So this is needed for the simulator, because if we don't put this, when the simulator will calculate the simulation, at a certain point it will have to deal with big numbers, too big than the ones the computer can deal, and it will throw you an error, something like the divergent calculation for frequency whatever. So these are tricks that we have to know, and this is the reason for which when you simulate something, you can't normally expect to simulate exactly the circuit you have mounted, because the numerical algorithm cannot work with infinitive numbers. So then the question is, but how can the circuit work? So the physics can really works with amplification factor which are extremely high, that tends to infinitive. So the answer is not really. But we have to remember that physical components cannot have extreme values like zero resistance or infinitive resistance. There are the so-called parasitic components. So, do you remember the example when I touched the leads of the multimeter with my hands, and the multimeter was measuring a very high resistance, the resistance of my body? Of course, if I touch any part of any material body, or even in the air like this, also the air has a certain resistance. Here we have the breadboard, and the breadboard also has a certain resistance that can be very high, in the order of the megaohms, maybe hundreds of megaohms, but not infinitive. Also the capacitor itself, it's not a perfect ideal capacitor. It will have a certain internal resistance which is something, now we don't know exactly what. So this thing is capturing the real implementation of the components, but of course the simulator doesn't know about the real components. The simulator is just doing mathematical calculations, so we have to include those parasitics components in the model sometimes, otherwise the simulation, as we say in the electronic jargon, will explode. So to make a long story short, this is why we need sometimes extra components to make the simulation working in a more precise way. Okay, now that we said this, we can try to conclude this part, theoretical part of the circuit, by try running a simulation. So you can try to do this. Here you have in the menu there is inspect, there is this simulator. So in this simulation we need to put some parameters. So I suggested here something you can try. For instance, what we will do is a so-called transient simulation. In a moment I will explain what it is. And in order to have it run, we have to put some parameters. The time step and the final time, those two values. These are in nanoseconds and milliseconds. So what is the time step? The time step of a simulation is the delta t. So the computer cannot solve analytically the circuits. It makes a simplification. So for instance, instead of being dealing with a continuous variable, it discretizes it in chunks of time and also voltages and whatever. So the simulation proceeds step by step in order to transform everything in algebraic equation that the computer can mangle. So if I go here and I try to simulate, then there is a panel that opens, the SPICE simulator, the one that we have spoken last time, so with the SPICE models of the component. And then I have to go on settings. Here I can run different types of simulations. The AC simulation, which is a simulation that takes into account the sinusoidal stimuli, the DC, the operating point, which is similar to the DC for let's say direct current, and what we do now, which is the transient. So here we can specify something like this. Let me put numbers. Okay, so 100 nanoseconds, the time step, so 0.1 microseconds, and let's try with 5 milliseconds. So the time step has to go according to the Shannon-Nyquist theorem that we studied during the theoretical part of the course. So if I expect to have a signal amplified by this amplifier in the range of the milliseconds, like neural pulses, then I have to make a much smaller time step, otherwise I will have this aliasing problem. So we have to fill this table according to what we know we put in the schematic diagram. Then I put 5 milliseconds as final timer. I press OK, and then I run the simulation. Okay, now the computer is computing. It takes a while. So the speed might be different. So now I'm connected with remote desktop to, let's say, my big computer, which is let's say powerful. I tried doing this on the laptop. It was much slower because I have an old laptop. So in case you want to try on your computer, and in case you see that this simulation is quite slow, you can try, for instance, to reduce the 5 milliseconds time, and so it will simulate less data and it will be faster. So now what we can do is to attach a probe in our schematic. So the simulator, what did it do? So it assembled a set of equations. If you remember, we did something similar when we were doing this node analysis during the theoretical part of the course. We tried to apply this mesh method in order to compute the voltage at every node at the circuit, and this is what the simulator did. So it takes into account the netlist representing the spice model of the component. If you remember in the datasheet, all those transistors and resistances internally implemented in the microchips. Then it took into account all the external components we attached, all the sources voltages, and in a few seconds it did something that we probably can never do in our life because it's too much computation. But in principle it did the same thing. So now we take the probe and we go, for instance, at the output of the signal. So you see, if you hover the various nets, they will be highlighted. So once they are highlighted, you can click. Now I go back here. Let me make it bigger. Okay, here you see the result of this simulation, 5 milliseconds of simulation. So let's try to understand it. Maybe like this, it's too big. So here we have one axis, the axis of voltages. Then on the horizontal axis we have time. And we have our signal. You see that the signal is not perfectly smooth because there are noise sources in our circuits. Then, just to roughly understand what we did, let's take a rough measure peak to peak from this output sinusoid. So it goes from 1.86 volts to 2.52 volts. So let's say it's about 1 volt of amplitude, a little bit less. So let's go to the schematic diagram. So in the schematic diagram, I put as a, let's say, fake neuron, a sinusoidal voltage with these parameters. So let's try to right click it, properties. So here is the place where we put those parameters. We right click it and then spice model this thing. So this thing means that for that fake neuron we took a sinusoidal generator with a 0 offset, so 0 volt as offset, so that the pedestal level of the sinusoid we choose to be 0. So this thing is alternating positive and negative respect to a center line. The amplitude of this signal is 100 microvolts, which is something that we might expect for an extracellular recording, and 1 kilohertz of frequency. So from a signal of 100 microvolts, now we have a signal at the output of about 1 volt. So it means that this thing has amplified a lot our input signal, because 100 microvolts is 0.1 millivolts, and we have a volt, so it's something like an amplification of a factor of 10,000. So then let's see what we have as a noise. I put a signal which is a sinusoidal of 50 Hz, which is this nasty signal we have usually to suppress in Europe, because in US is 60. And the amplitude of this external noise is 100 millivolts. So you see the signal that we are adding as noise is 1000 times more than the signal generated by our neuron of interest. So there's huge amount of noise. But this noise is applied to both inputs. So the amplifier is doing its job in a quite good way. So it's completely suppressing this noise and amplified only the difference. Then another thing that we can notice is that sinusoidal signal is not, let's say, completely stable. You see that it's drifting up. So this thing is because of the transient simulation. So the components, when we turn on the amplifier, they have some, let's say, characteristics. For instance, you know that a capacitor can be charged or discharged. So if I apply a battery across a capacitor, like this, if I charge a capacitor, then when I remove the battery, the capacitor will stay charged. So there is an initial state of charge of the capacitors that will influence the time simulation. And so all the capacitors needs to reach a steady state in order to have a steady signal at the output. So if we try to do something now just to see how it goes, now I want to go to the simulation parameters and instead of 5 milliseconds I put let's say 20 maybe. Let's put 30. I don't want to put too much because then it takes too much time. So I click OK. I simulate everything again. So now I'm repeating the simulation, but for a long period, just to have an idea of what the trend will be for this signal. So let's wait for a few seconds. So now we are at 2 milliseconds of simulations. Let me zoom here. Okay. So for each time step that you see running here, the simulator is computing an enormous amount of equation, solving all the voltages and all the nodes in this circuit. Okay, 5 milliseconds. It takes a while. So from this you also see the importance of understanding what you are simulating. So the simulator is not something that you just push a button and then you have the result. Because if you don't instruct it carefully, maybe you will wait forever. Maybe it will hang because you don't put those, for instance, 2 resistors that we put across the capacitors in order to mitigate this divergence for high frequencies. So simulators are not something that you can use blindly. You have to know what you are going to simulate. So it's always a better idea to try to calculate something at least approximately, just to have an idea of the behavior. And then the purpose of the simulator is to simulate the circuit exactly. So that's the advantage. So this circuit, most of the time, because those simulators are very precise, will capture many features of your real circuit. Okay, we are almost there. 15 milliseconds. So we put 30, so we have to wait for other 30 seconds probably. Okay. So meanwhile that this is computing something, I can tell you also something else. So you can add also other signals. Now we can't because the simulator is running, so we have to wait for it to be finished. And you can plot many things simultaneously, all the nodes of the circuits, also currents. So it's very handy. You can try to do a lot of things with the simulator, and especially when you work with high power components like high power transistor, such kind of things, for instance motor drivers, that will save you a lot of let's say miscalculations or components that you might break because you made a mistake. So it saves a lot of time and a lot of money in saving by destroying components. Okay, we are almost there. Two point five, no, 56 milliseconds. '57. It's like the countdown. 58. Okay, 59. Okay, that's it. Good. Okay, so now you have a better idea of what's going on in the circuit. So this time transient time simulation, it is telling you another thing which is sometimes interesting, what is called the settling time of the circuit. So you see that from this chart now the trend has been stabilized after, let's say, 20 milliseconds, 20-25 milliseconds. Then if you run the simulation for a longer time, you will see that this value here, this let's say pedestal, it stays stable at that level. So this is interesting because in this case what you know is that you can't just turn on the circuit and rely on the data from the very beginning, because it takes a while for the circuit to reach a steady state. So in this case the steady state is reached after only 20 milliseconds, but I mean this is for this circuit. Maybe you do something else and it's different. So it captures interesting features. Okay.